Good day, everyone, and welcome to another interesting session, which is going to be delivered by Mr. Giovanni on controlled polarity transistors, higher density and better control. And this particular webinar is part of an year-long series which the IEEE Electron Device Society New Delhi chapter is organizing jointly with Deen Upadhyaya College, University of Delhi, under the aegis of Department of Biotechnology Star College program. And in this, we will be able to hear out some of the leading experts and luminaries in the Electron Device Society, and they'll try to share with you their experiences, their research activities, and which you'll be able to understand right from an undergrad level to our research or the faculty members who are working in this particular area. Professor Giovanni is a well-known figure in Electron Device Society, and he's a research scientist in electronics and computer science. He's credited for the invention of the network-on-chip design automation paradigm and for the creation of algorithms and design tools for electronic design automation. He's a professor and director of the Integrated System Laboratory at EPFL Switzerland. And previously, he was the professor of electrical engineering at Stanford University. He was director of the Electrical Engineering Institute at EPFL from 2008 to 2019 and program leader of the Swiss Federal Nano-Tera.ch program. He holds a nuclear engineering degree from 1979, MS and Ph.D. degree in electrical engineering and computer science from University of California, Berkeley, 1980 and 1983 respectively. He's a fellow of ACM, AAAS and IEEE, a member of the Academia Europaea and an International Honorary member of the American Academy of Arts and Sciences. His current research interests include several aspects of design technologies for integrated circuits and systems, such as synthesis for emerging technologies. He's also interested in heterogeneous platform design, including electrical components and biosensors, as well as in data processing of biomedical information. He's the author of Synthesis and Optimization of Digital Circuits, a book published by McGraw-Hill in 1994, a co-author and or co-editor of 10 other books and over 900 technical publications. His H index is above 100, according to Google Scholar, and is also a member of the Scientific Advisory Board of IMEC Belgium and ST Microelectronics. He's a recipient of the 2022 ESDA-IEEE CEDA Phil Kaufman Award and the 2019 ACM SIGDA Pioneering Achievement Award and several other awards. With these words, I now invite Professor Giovanni to kindly share his screen to deliver his talk.
Thank you. Thank you very much, Najib, for inviting me to give this talk. It's for me an honor to be there. I've been working at the boundaries between electronics and computer science for over 35 years. And what I'm going to tell you is an experience we had over the last 10 years on a sequence of devices and on the related design methods that originated from them. But since this is a celebration of the transistors, we'll be mainly talking about transistors during this talk. So that's an outline of this presentation. I will start with a recent history of the transistor and established technologies present in the last decade, talk a little about emerging technologies and future transistor technology examples. Then I'll talk about the controlled polarity transistors and what we mean by that, how that is done, what's our experience with it, and then about design. What do you use it for? What can you use it in the future for, since it's not used commercially at present? It's used only in research, and talking about physical design and logic design. And eventually, I will conclude. So if you look at the last 10 years, most advanced manufacturing technologies have geometries in the 3 to 30 nanometer range, at least in terms of what is called a node. Basically, we go from the 3 nanonode of TSMC to the 28 node, which is still quite used. And if you look at what's available in advanced nodes, there are basically two groups. One is the tri-gate, which is the FinFET, it's just a matter of naming. And the other one is FDSOI, which stands for fully depleted silicon on insulate. There's the issue of downscaling geometries. That's very often discussed. In my opinion, that's still effective. We are going to see some more downscaling in the 10 years to come. But practical result is that in the end, you don't have much of a size reduction of the entire chip if you downscale beyond the 3 nanonodes, but you still can achieve lower power consumption. So that's still positive, and that's why some downscaling is still happening, at least in the 3 most advanced fab that we have in the world. And of course, we have to keep an eye on the emerging nanoelectronic technologies. There are new materials, there are new devices that can be used for processing and memory. So I will start a little bit by the beginning. I don't know what kind of audience we have all together. So some basic thing, about 10 years ago, we moved from bulk technology to the FinFET technology. And the idea is that by creating fins on silicon, you can see the 3 vertical fins in the picture on the right, you have more area under the gate, which correlates to have better charge control inside, better charge control in the channel. So if you scale down the devices, then you can still have a good value of the I-on over I-off, which is the current when the transistor is on over the current that you have when the transistor is off, that is the leakage, which is a main parameter to tell how the design is effective. And what the result with that, from 2 simple plots for the same gate voltage, then you have less current, and also you get the same gate delay for smaller operational voltages, which allows you, of course, to scale down the voltages, and that's very beneficial. The other device which is used these days is the fully depleted SOI device. Here you see a sketch where you see that the transistor is built on top of a layer, which is the barium oxide, the box, and you have a thin undoped channel, which is fully depleted. And the fact that the channel is contained allows to have fairly well-characterized, well-operational devices. And then you can also control the power consumption by doing body bias. And that's actually a big plus of this technology, which is mainly applicable in the low power domain, like, for example, Internet of Things. So here you can see 2 plots coming from STMicro, and you can see that here you have the energy efficiency versus speed, and the higher the curve it is, the better. And you see that the light blue curve is actually higher than the one corresponding to the bulk non-SOI type of technology. So this is basically where technology is today within industry. Actually, this picture here shows how you can actually bias, your bulk in order to adjust your thresholds, and that's actually how actually you can have further power reduction that can be done dynamically using this bias. Now, other things that are interesting is to see what are the emerging ways of building transistors. These came up over the last, again, 10 years. And one basic fundamental model is the one of silicon nanowire. You have a wire of silicon with a gate all around that allows to have a very good control, again, of the charge. If you think in a FinFET, you have control over 3 sides. Here you have it over all the sides. And this type of devices allow to have, again, fairly high ion over I-off ratio, and that's why they're interesting. So these devices started appearing, even at the beginning of the century, then for the 10s, and then they evolved, and there are many ways of doing that. One is of creating, horizontally stacked nanowires. You see a stack of about 10 of these nanowires that you have. That's interesting because also according to how you contact them, you can have the equivalent of transistor with various width. And if you can compare that structure to the FinFET, in the FinFET, you have a vertical slab that goes through the gate. And in the case of the nanowire FETs that are vertically aligned, instead of having this slab that goes through the gates, you have many of these wires actually going through it. That's an interesting picture coming from Intel that shows some cross sections. So on the left, you see the FinFETs, and then in the center, you see the nanowires. These are fairly circular nanowires. On the right is what is the technology that we're using. We still have wires, but this time they're squished. You can see that the cross section is an oval, and that's why they're called sheets. This is the nanosheet technology. And this took time to get into production, but now Samsung is producing it in the 3 nanonodes. So actually, it's very much state of the art where we are today. So if we want to look into the future, into the crystal ball, that's kind of hard, but I'm actually leveraging an image produced by IMEC. IMEC is a center that always has been looking at the technology evolution. We're more or less at the center of the picture, where we have the transition from FinFETs to gate-all-around nanosheets between 22 and 24 today. And the idea is that going on, there will be a variation of the nanosheets, which is called fork sheet. And eventually, the technology that is projected is the CFET, where we will have still some sheets with gate-all-around, but then we will have superimposed P and N transistor. And all this is, of course, in order to make a stack that is as compact as possible. But again, here we are talking about 10 years from today, and very much looking into the crystal ball. Now, another object that it's always been interesting for me is the vertical nanowire, where the development has been very much in the domain of physics and less in the domain of engineering, because it's a difficult object to deal with. The idea is that you would fabricate the nanowires vertically, still with a gate-all-around. This is fully compatible with CMOS. And then it gives you a structure where you can have a higher device density, because actually you can imagine 2 planes, and in between these 2 planes, you can have either vertical connection or transistor with nanowires. So you will have actually a lot of density of these devices. The question is, it's much more complicated to build them. There's a lot of activities of that in Toulouse. And again, in my opinion, this is still a technology which is promising, but it's further away from practical application, while the horizontal nanowires or nanosheets, even if stacked, it's basically the bread and butter for the upcoming technologies. What about future technologies? What's there on the map? Well, of course, there are many ideas that are around. I'll talk about 2 because are technologies that I'm familiar with. The first one is the one related to having carbon nanotube transistors. Well, a carbon nanotube, or a CNT, is the roll-up sheet of graphene. They can be synthesized, they can be grown. Typically, you want to grow them because of regularity. And then you can create a process in which you have the CNTs on top of silicon, and then you pattern them, and you pattern them in a way which is similar to what you would do for CMOS, but where in the end you will have the channel, the active part of the transistor, actually made of carbon nanotubes. And here the inherent advantage is that the CNTs can have a mobility that's 100x as compared to silicon in bulk. So starting from this piece of data and considering all the possible engineering non-idealities, you have devices that even though they are scaled down, they can provide or sink currents that are much higher as compared to the silicon. So you will need less buffering. So at least in theory, you have devices that are fairly efficient and useful to look at, especially if you want to scale down in the nanometer range. Now, one of the biggest problems with CNTs has been handling imperfection. In the beginning, the devices built with CNTs, and I think in principle with those created by Philip Wong at Stanford, and they had a lot of non-idealities due to interruption as well as curling effect of the nanowires. But with the years, within the, let's say, the 2010s, then the way of producing chips based on carbon nanotubes, even based on a tape transport of the nanowires from the growing substrate to the substrate that's used for the computation, got better. So that led actually to the design of a nanocomputer that was done with CNTs. This actually goes back to about 10 years ago, and it was a big success. It was a very simple RISC with about 120 transistors, but still it managed to be working. It was showing actually how this device could be effective. Well, this is rather, old, I would say, results. It showed the feasibility of this technology, but the recent result is fairly exciting. This is the work done by Hills and Schulacker at MIT. Hills was his student, together with analog devices, and Schulacker, we worked before with Subhashish Mitra and Philip Wong at Stanford, and they were able to create a 16-bit RISC-V with about 14,000 transistors that are both P and N nanotube transistors, and this is done over several layers. And this picture here actually shows how you can layer the various parts of CNTs to eventually provide a functional chip. So this technology now has some maturity since it has been shown to work for something which is reasonably interesting and at scale. And in my opinion, the advantage of this type of process is that it's a relatively low temperature process, so that you can actually stack functional layers one on top of each other, which is, on the other hand, very difficult for doing that on silicon. When you think, silicon transistors, you're trying to layer them to have this so-called sequential 3D integration, like, for example, done at Leti. You are always confronted by the fact that putting a layer would harm the layer underneath, and you need to have a special type of materials that may not be that effective, for example, in terms of resistance. While you can do this 3D stacking with carbon nanotubes just because of the relatively low temperature of the process. Now, other type of technologies that are of interest to us are the 2D technologies. Sometimes they call it flatronics or flat electronics. One prominent device is the MOS2 transistor, where MOS2 stands for molybdenum disulfide transistor. And that was the first time demonstrated by Andreas Kish. And this is done in a single layer or a few atomic layer. And again, it has a fairly high ion over I-off ratio for these devices. But it's done, this works mainly for N-type. So it is somehow a disadvantage the fact that it's hard to do P transistor in MOS2, so it's hard to do complementary logic. And we all know that CMOS actually took over the world because it's complementary, and so it has very low or actually zero static power dissipation. Nevertheless, it was a few years ago, there was the first design of a RISC, again, with these technologies. It's very simple processor, but it shows that this can work. And interesting enough, they came out with more or less 120 transistors, like in the case of the carbon nanotubes. It's a different design, a different architecture. It's basically a demonstrator of this technology. Now, keep in mind that the sizes of these devices, typically, it's much, much larger as compared to what you can do with CNTs and with advanced silicon. So there's still a long way to go for this flat electronics, flatronics, or 2D electronics before it becomes effective to be used. Another factor that I'd like to mention that, again, in the case of this technology, the process is a relatively low temperature process. So again, this type of materials are materials that can be stacked on top of each other. Okay, having said this as introduction, I want to talk about the controlled polarity transistor experience, how we did the design, what are the advantages and disadvantages of this device that actually departs from other devices. So this is the overall scheme where you see the structure in green with source and drain. You see the nanowires that are hidden behind the first gate or polarity gate that are horizontally stacked nanowires, and then a control gate. So in the end, what is it? It's a transistor built with gate-all-around nanowires, and where you have two gates, one polarity gate and one control gate. The control gate is the standard gate that you would have in any transistor, while the polarity gate biases the Schottky junction that you would have at the end of the nanowires at the contact with the metal, and that actually will determine which type of carrier is allowed to go through the wires themselves. So how does it work? This is the symbol for that. It's a transistor where the bubble, which is what differentiates an N from a P transistor, is programmable by this polarity gate. And if the polarity gate is set to a 0, and say here we use 0 and 1 to abstract what are the operational voltages, then we have a P FET. If it's set to 1, we have an N FET. So we have two transistors with the same structure. And we differentiate this by doing electrostatic doping. One advantage of that, you don't need to do doping to just privilege a carrier inside the channel. You can actually do that with a field. So again, you have a device that can be programmed even from high level. Think, for example, an FPGA type of structure. And even from high level, you can program the devices. And so you can have interesting functions that can be built. Another thing that is very important is that a transistor is a switch, as was the triad. And here we have a switch which is activated by a comparator. Actually, two values are compared, and according to their equality or inequality, again, it's exclusive OR, then you would activate the switch, you turn the switch on or off. So there is a potential higher functionality inside the device as compared to a single transistor. These are designs of things that we did through the years. Here you see actually the nanowires that are in green. That's courtesy of Photoshop. And then you see actually one gate that it's in purple. Here we'll see the second gate that it's in brown that's built around it. And these are some of the sizes that we had. We went through different runs with, of course, decreasing scaling of the devices. That's a cross-section of what we were getting inside the lab. That shows that actually we could have more or less nanowires of a cross-section of 20 nanometer. This was done inside a university fab, a fab typically done for silicon and standard silicon. So this was probably the best that we could achieve out of the fabrication facility that we had. Now, how does this device work? There are 4 cases corresponding to the values of the gates. And by the way, I use these values as 1s and 0s, as the logic 1s and 0s. But after some process tuning, we were able to make actually the high voltage very close to 1 volt and the low voltage is 0. So actually the 1s and 0 represents not only the logic values, but the type of voltages that we were able to use. So if the programming gate is 1, and therefore we have an N-type transistor, and the control gate is 0, we have the bands as shown in here. And of course, there are bumps that impede the carriers to go through, and so the device is off. If the programming gate is 1, that is, we have an N-type transistor, but we put the gate to a 1, then the gate will flatten the bands, and then the electrons will be able actually to go up the potentials, as the way we'll have a current running through the device. If the programming gate is 0, we have a P-type transistors, and if the control gate is at 1, again, we will have the bands in such a way that there will be no conduction. And if we have programming gate at 0 and control gate at 0, then we will have holes that actually can go through and a corresponding current through, so the device is on. This is a simplified way of what happens. These are plots that actually shows the superimposed P and N transistor. This is not the only way to build these devices. This is the one that we played with. Keep in mind that the same thing can be done over a FinFET by having, again, 2 types of gates around a FinFET. And also keep in mind that another type of devices that are similar, and in my opinion, more efficient, have been made in Dresden by using only 1 polarity gate. That is, you have the polarity gate only on one side, and one side is what you need, because what you really want is that you have a nanowire that can carry electron and holes, and then you use the polarity gate as a way of stopping one type of carrier. So you have an ambipolar channel that you make it actually one of the 2 possible carrier type device, and that can be done by just doing this gating on one side. So the Dresden group actually achieved some devices that are better than the one that we've done, and actually they went on working on it for a longer time. There are other things that can be done, you know, some biasing schemes can be done to handle and to build devices with a steep subthreshold. And also you can play with multiple threshold voltages. There's also the question to say, well, since you have 2 gates and 1 gate is a U-shaped gate that goes to the right and to the left side of the device, and what about splitting them? So you have end up with having 3 independent gates, and you can consider them as independent. So what can you do with a device like this? Actually, it's interesting because you can increase the level of programmability of these devices. So you have 3 gates, you have 8 possibilities, and 2 don't really make sense, but the other 6 do make sense. So the first 2 are the one that I've designed before. That's to have a P transistor or an N transistor, which is on. And then 2 other configuration will tell you that you have an N transistor or a P transistor that it's off. But if you make the bias of the left side different from the one that you have on the right side, then you can have a device that it's off, but it has a higher threshold voltage. So this, again, it's a concept that's interesting, has been tested in researchers, not, in my opinion, tested on large-scale designs. But as you know, there's always the issue of having inside the chip the transistors that are faster and more leaky, and the one that are slower and less leaky. and you use in design this type of transistor or the corresponding standard cells to implement the critical and the non-critical path of your system. And in this way, you can make everything programmable. You can make it programmable from the top. You can decide post layout also which cells should have a higher threshold or lower threshold. So this is a very interesting concept. Another point of information which is interesting, what can you do with in other type of materials? There is work actually on carbon nanotubes that are polarity controlled. Some of this work was done in Lyon by the group of Lyon. I don't have slides on that, but that was the first type of devices that were shown to be ambipolar. And this is some preliminary work that has been done on two-dimensional controllable polarity transistors on wolframium diselenide. Well, we don't use MOS2 because MOS2 is with MOS2 it's hard to do the P transistor, but with wolframium diselenide, you can make devices that are both P and N, again, with the same principle of biasing. Of course, these are experimental designs. They're done by using the material in flakes, so it's fairly imprecise, and also the range of voltage is quite large. Now we're swinging from, plus to minus 10 volts. So this is still far from doing something practical, but the technology for this type of materials, not necessarily tungsten diselenide, but tungsten disulfide has actually progressed quite a bit. Next, I would like to show you why this type of devices are interesting. What can you do with them? How you will handle design? And actually, most of my work is on design models, design tools, and it's really interesting to link this type of devices back to the way in which you design and to see why you would like to have them. So let's start from the first principle that says that a three-terminal transistors are switches, and basically a loaded transistor is an inverter. Now, the controllable polarity transistor compares two values, and so the loaded transistor is not an inverter, but it's an exclusive OR, or a comparator. And that makes it interesting because the XOR is a device that typically requires more transistor. The XOR is a gate, logic gate that requires more transistor to be built. It's, in many technologies, you try to avoid them. So the control polarity transistors have an intrinsic higher computational expressiveness as compared to standard transistors, and that can lead to more efficient data path design. Keep in mind that, of course, the number of terminals must be compensated by smart wiring, because if you have more inputs to a transistor, you have to wire them, and wiring is typically the killer of any advanced technology, because that's where you touch the ground with reality. But these devices allow fine-grained programmability. So again, we see various technology, the silicon nanowire, the 2D FETs, and also the CM FETs. I said it's the same thing. These sketches, basically, you have two values, you compare them, and these activate the switch. So what would you do once you have to design standard cells? So if you have simple functions, like inverter, NAND, this is what's called in logic negative unit function, or monotonically decreasing function, because when the N part turns on, and the basically you would have the output values either staying at the same level or just going down to zero. So it's easy to build this function using controlled polarity transistor, because you build a pull-down network and you build a pull-up network by having a choice by programming these devices to be P or N. So there's nothing particular in there. But if you look at bi-innate functions, so functions that would not be monotonically decreasing, like, for example, the case of the XOR, then by combining in a smart way this controlled polarity transistor, you can have a logic gate, which is fully swinging from VDD to ground, just built out of 4 of these devices. So this is very, very interesting. So how would you do the physical design with that? So in order to reason about that, you have to connect the notion of electronic device to the notion of topology, because that will lead you to the way in which you see how you would embed the design into a plane and you connect it up. So starting from this structure that is sketched, one can derive the so-called dumbbell-stick diagram. So remember that the notion of stick diagram has been around in design for many, many years. The idea is that you use colors to indicate layers. And here the transistor channel is in green, as it was many years ago, the so-called diffusion that then became an implant in CMOS. And here you have 2 gates. One of the gates, as traditionally is used, is the red, like for the polys, the control gate, and we use another gate that it's done on with blue. And when you have devices like this, then you have 2 issues to deal with. One is the fact that you want to pair transistors. So you want to have control gates that get connected together. And if you remember in CMOS, you know, one of the way in which you design the standard cells is that you try to align the transistor so that the P transistor stay on top of the N transistor so that you can connect the gates just with one single element of polysilicon. So that's the same thing. But here you have to deal also with the other gates. So you have also the notion of transistor grouping, where you want to privilege the fact that you want to connect together the polarity gates rather than the control gates. And there are trade-offs in between. But to give you an example, it is possible out of these dumbbell-stick diagrams to build cells that are sketched as the one that you see on the top of the picture, which I would call the master cell, that involves actually 4 transistors, and it has 2 control gates that are aligned, G1 and G2, and the polarity gate that are on top, on the bottom. And then according to the polarization that you have, you can get different things. So in the bottom left picture, you will see that by putting a fixed polarity on the 2 control gates, you will get an AND2. If you invert these polarities, you will get an OR2, And if you use the configuration on the right, you will get an exclusive OR. So you get NAND, NOR, and XOR out of the same primitive, which is highly compact in terms of size. Now, how would you put logic into this? There are many ways of doing it. And one way of that is by making an abstraction of these transistors, which are controlled by a comparator. Just for those of you who are familiar with logic design, the binary decision diagrams are quite often used, and the diagrams where you have at every node the equivalent of a multiplexer, and you will switch to the right or to the left according to a value. Here we have a more complex data structure to represent logic, which is called a biconditional binary decision diagrams, where you have, again, a decision based on comparing 2 variables. So in mathematics, we could say that we do a comparison, and then we obtain the generalized cofactors with respect to the values of this comparator, and we have an expansion as shown in the formula here, that it's a generalization of the Shannon expansion. So if you represent logic like this, then you have this type of continuity. You have the logic model, you have the electrical model, which is represented by a multiplexer, which is driven by a comparator or an exclusive NOR, and then you have for each node the corresponding transistor level of limitation that then can be realized by a block like this. So there is inherently with these cells a direct synthesis procedure that can map functions in logic represented through these diagrams by BBDDs that then have an implementation in terms of gate in this structure here. This is an example of a gate array that is built out of this type of devices that then can be personalized to have functions. Alternatively, of course, one can work using standard cells and build a standard cell of logic, and then you would actually use mapping tool to that cell. Here I have a picture that shows actually a different type of technologies as to show you the notion of a standard cell built with this type of transistor. This was done at IMEC with tungsten dicyanide, and it's a very simple cell library that has inverter NAND and OR, and then has the XOR and the majority gate. So this actually serves an introduction to the last part of my talk. And in order to get to that, I like just to make some key points, in the last few slides, I showed some methods to deal with multi-gate transistors, and that actually can implement the XOR function and can binary function very well. What's interesting is that by combining these transistors, you can have the three topologies that you see at the bottom: the 2-input XOR, the 3-input XOR, and the majority tree function. The majority is extremely important. That's the carry function that you would have. And once you have these gates that are all very compact, you have the basic building blocks that you need to do addition and multiplication. And at this point, you can just take one step back and think of what you want to do. You see, for example, today, everybody is thrilled about AI, machine learning, and systems that do that, and where a lot of operations go back to arithmetic, comparison, XORs, and majority. And they get implemented in a much better way if you use this type of abstraction as compared to the NAND-NOR abstraction that we have seen through our careers. We have designed for decades with NANDs and NORs in mind. Most of the cell libraries are implementing AND/OR inverters, which are extensions of NANDs and NORs. And this actually creates an inability, this limits the ability of doing arithmetic function in a compact way, for example, by using tools that you would need when you actually don't design a simple adder or simple multiplier, but you need to have something ad hoc, like, for example, for the current chips. So the idea is to use the motivation of these devices to think in terms of majority gates, XOR gates, because these are key to all arithmetic functions. And also the majority model, the majority operator is a native model for other technologies. Like, for example, you have in non-volatile logic in memory when you deal with, for example, oxide-based or phase-change RAMs, and also in the superconducting domain. So the fact that with new technologies, and controlled polarity transistors is one of these, you can design well XORs and majority, actually can lead you to have different type of design. And it's interesting how everything actually turns around and people in the end start thinking in the same direction. I have here a citation from Don Knuth in the recent volume 4A of the R Computing Programming, in which he indicates the majority function as the bracket of XYZ, and he says that it's probably the most important ternary operation in its entire universe, because it has amazing properties that are continuously being discovered and rediscovered. But simply put, if you have a macro that's compact, that can do majority, if one of the input of the majority is stuck at 0, stuck at 1, you're building the AND or the OR gate. So you have a building block that is programmable that can do the basic operation that you need. And this type of operation can be characterized very well by graphs that can implement function. And now you forget about the classic diagrams where you have AND or the BDDs where you have multiplexer the node, but you have the majority function, which is nice and symmetric, and that can implement function. And of course, you would need to have inversion, complementation, that's here represented by the bubbles. So once you have this, then you have to think in terms of different ways of thinking. I just show you a few pictures here. I don't want to get into the detail, but you can build an algebra based on the fact that you want to exploit the majority function and its properties that relate back to commutativity, distributivity, and inverter propagation. And you can use this property to design circuits using properties for rewriting circuits. So given a circuit that are represented in this way, they can be rewritten. And then also they can be made compact because there is an inherent redundancy built into the majority function. And so you can have ways to quickly compact circuit design with that. I will spend no more time in talking about this because this goes beyond what was the purpose that was to celebrate the transistor, but to say that if we think of transistor structure that are more complex, we pay a price for the complexity of designing the transistor itself, but we gain by having better means for designing something that's more complex. And at the end of the story, I also would like to point out what we were able to show after 10 years of research in this, and this is a result of 2-3 years ago, that if you take your logic and you cast in terms of majority and XORs, and then you develop specific tool for implementing it, that's good, of course, for devices that have the native abstractions in terms of majority and XOR, but it's also very good for devices like CMOS. So to some extent, if you use majority and XOR as a modeling tool for standard logic built in CMOS, then you can transform the logic and make it 15 to 20% faster, 15 to 20% faster, as compared to what you could do it by using standard tools, just because you have a much wider space of applying reduction of circuits using these models and the corresponding algorithms. So with this, we come back in full circle. To some extent, the experience that I wanted to describe in this talk started by having devices, nanowires that are efficient because of gate-all-around, controlled polarity because they have more functionality, having models for this controlled polarity transistor, demonstrating that you can have design tools for designing with this type of technology, and then applying them back to CMOS and showing that this is also a way of doing things efficiently in CMOS. And this actually leads me to knowing the conclusions of this talk. Computing is evolving rapidly. We have never seen evolution so fast of computing as in these days, and permeates all activities of everyday life. And we are still based on von Neumann architectures, switching theory in silicon devices, but there is a tremendous opportunity of using new materials and devices to change the physical substrate of computation, the primitives that we use in computation, and make it more efficient and broader in scopes. And in order to make that happen, progress will require strong coordination of technology and architecture, as well as design methods and tools. Thank you very much for your attention. I would like to thank my colleague Yusuf Leblebici, who's now at Sabanci University, Pierre-Emmanuel Gallardon, who is at the University of Utah, Davide Sacchetto, who is at CM, Michele De Marchi at Espros, and Jan Zwang at Huawei. Without their work, all these ideas could not have been developed so far. So thank you again for your attention.
Thank you. Thank you very much, Professor Giovanni, for taking us through this 4 decades of your journey in about 50 minutes or so. I must appreciate your timely intervention and the contributions which you have made in the area of electronic design automation. Well, there are a few questions which have been shared by the attendees. Let me just share my screen so that everyone can see that. I hope you're able to see the questions.
Okay, sure.
Yeah, please go ahead.
Let me go from top to bottom. Can I comment about the reliability of controlled polarity transistors? Well, to be quite frank, we have not been doing research on the reliability of these devices themselves. So there is very little comment that I like to do it, and I like just not to make a story out of it. I would say that I don't have specific data on that. What is the fundamental need of nanowire and nanosheets? There is a fundamental need because as you scale the device down, you want to have devices with very high ion over IOF ratio. You want to have structures that are better than FinFET. If you cannot design better than FinFET, then why you should do anything else? And we see that Samsung is doing it with nanosheets. We see that TSMC has its 2 nanonode plan with nanosheets. And so the need for that is that you have a compact and better control structure as compared to FinFET. So that's actually what drives the shift to using this type of technology. 3, sir, can you comment about the ambipolar effect of controlled polarity transistor in comparison to, I don't see it, TFETs for analog application. It's true that these controlled polarity transistors have ambipolar effects, but we don't use any of this ambipolarity. We basically kill the ambipolarity by doing a biasing so the device will be P or N. Keep in mind that very often the ambipolar effect is something that's not desirable in digital logic. Here we are talking about digital logic. We have never tried to use these devices within analog logic. So my comment of that is that we use ambipolar devices that then are transformed into P or N. 4, at present, ReRAMs, Oxfam, resistors are gaining widespread attention for marine application. Can you comment about the viability of controlled polarity transistors to these devices? Well, I think they are very different. So if you take memristors are basically 2-terminal devices, and here we have 4-terminal devices. So memristors are going into the opposite direction. And it's interesting because memristors have some sort of similarity, in my opinion, to Josephson junctions that are also 2-terminal devices. And they can be very compact, they can be very efficient memristors, but in the end, there is a little bit less control on that. ReRAMs, it's a generic term. In my opinion, OxRAMs are part of that. PCRAMs are also part of that. Interesting enough, if you use these memories for computation, the abstraction of this is still a majority function. That's why actually you can design logic and do computation within resistive RAM and OxRAMs, and it's possible to do logic in memory with them, exactly because you can force the various cells to behave like a majority gate. But of course, the market is different. I think there is a huge appeal towards ReRAMs, OxRAM, PCRAMs, because we can produce them in mass and in wide arrays. And there is a lot of very solid technology in terms of memory design and fabrication of large schemes. So that is that's a reality that we have today. So to some extent, I would expect that we will use more this type of memories in practice in the coming years than other type of devices, just because of their availability. Kindly explain the polarity control by inversion domain suppression in M-polar 3 nitride heterostructures. I would rather not answer question number 5, because that's not things that I've been doing myself. So I don't know how to explain this effect. The last question is van der Waal heterostructure in which layered materials are purposely selected to assemble with each other, or unusual properties and different phenomena to be combined and multifunctional electronics to be created. I explain how the reversible charge polarity control for multi-operation mode transistor based on again, this is work that I've not been working on. Maybe Manoj, you would like to comment on that? And
yeah, maybe we can pass on these things, because it's not directly related to the topic. Yeah, I do appreciate that. Well, thank you very much, Professor Giovanni, for taking out your time, and to other co-panelists, as well as to all the attendees who have been there with us for last about an hour or so. And on behalf of the IEEE Electron Device Society Delhi chapter and the host institution, the Upadhyaya College, University of Delhi, I would like to thank Professor Giovanni again, and hope that if he has any plans to visit India, then it will be an honor for us that if we can host him on a one-on-one basis sometime later this year, or maybe next year.
I hope to do that. I hope to do it.
Sure.
I've been to India a couple of times. I always enjoyed my trips to India. It's a wonderful country with wonderful people. So I look forward in the future, maybe not in 23, but in the coming years to come by.
Sure. Thank you. Thank you very much, sir. Thank you very much. Okay.
Bye.
Bye-bye. Bye-bye.